Okay, so Cora and I were invited to lead a small discussion now. I must say we have taken a lot of delay and I don't have a lot of time available anymore. The discussion was supposed to start much earlier, but of course the previous talks were so nice it would have been a pity to press the speakers. So I don't know, Cora, how you want to proceed. I've listed a few very general questions related to the previous talks on which maybe people can react. Maybe you have done the same. Would you like to start? Or
I have done the same, but please start and I will follow with some others if they don't overlap.
Okay. So I have two very general questions related to measuring neutrino masses. So there have been lots of forecasts on measuring neutrino masses with galaxy redshift surveys like Euclid, DAISY, Rubin. Of course, they are very naive, these forecasts. They don't model all the complexity of bias, uncertainties, etc. So I remember meeting Emanuele in a conference a few years ago, and Emanuele was saying, I don't really believe these bounds. I think it's very optimistic. It will be very difficult to measure neutrino mass with galaxy redshift survey. I would like to know if Emanuele and others have a similar point of view, or if their point of view have evolved. And maybe some people believe that it will still be very difficult with galaxy redshift survey, but with radio astronomy, there is more hope. So I would like to know the reaction of Emanuele and other people on this important question.
Thanks for blaming me. No, I guess my mind hasn't changed very much, I would say. Making a detection will certainly require combinations of best possible CMB data with best possible galaxy clustering data. And on the galaxy clustering side, I think we made progress in the sense that this sort of EFT of large scale structure kind of approaches now have enough complexity that you know the bounds are maybe worse, but they're more robust. So if a bound would come out of that plus CMB, I would be more confident. The other question is about photometric data. Those, yes, those I think are much more complicated to forecast because of systematics, right? In photo Z, and then the additive and multiplicative biases in the images.
So your main worries are on photometric redshift and on bias.
Right. Yes, I think the bias we made progress. We made a lot of progress.
And still, you presented some optimistic number for radio astronomy. Do you think that radio astronomy will be really free of these uncertainties and will be more robust?
On the piece of paper, maybe yes, right? Like the real issue is that until we do not have a detection, right? So anything that I say is very futuristic because we are orders of magnitude away from making a detection, looks like. So the time we have a detection, maybe all these things will become better understood. But until we have a detection, anything about radio astronomy, I think, comes with a huge question mark. I'm working on it because it's the true cosmic frontier. It really is the cosmic frontier. So I think we should work on it, but with the caveat that detections could be far away.
Wait, sorry, let me be provocative because I think that's what I'm supposed to be here. Are you saying that you would be pessimistic if you have the measurement of large scale structure and you detect neutrino mass, but you don't use EFT? However, if you use EFT, you would be completely optimistic? Is that your main worry, EFT versus some other way of, or you have other worries?
So for spectroscopic surveys, I think this, I don't see the reason why we should not use perturbation theory. Of course, I know a lot of people are working on things like emulators and machine learning ways of predicting the signal. I'm kind of I still like very much sort of these ab initio calculations. I think there are two things we can predict ab initio, and this is the clustering of galaxies with perturbation theory and EFT and the CMB power spectrum. So all the other things we cannot do ab initio. And so combinations of those two, I would believe much more than anything else. Yes, this is my.
I still think you are a bit pessimistic, because if you do a forecast for Euclid or Rubin and you try to limit the information to linear scales, it seems to me you can have error bars on the neutrino mass of the order of 0.02 electron volts.
Yeah.
No, no, for sure you can with the photometry. Absolutely, yes.
Mhm.
Yes.
Maybe other people have reactions on this question, on this general question of the robustness, feasibility of measuring the neutrino mass.
Or
wonder how
perhaps
much. Oh, sorry.
No, I was going to add a related question is what would be necessary for you to trust such a detection? Would you like to see, what would you like to see besides, you know, a measurement in the large scale structure? Sorry, Julien, go ahead.
I think I was going to ask something like that in the theory direction. Like, how much do I have to expand my theory space, my parameter space, to convince myself I've seen neutrino masses and not something else in the background? Because we know neutrino masses are degenerate with H naught, they're degenerate with dark energy. So how am I convincing myself I'm actually seeing, like, if I could see the step, like the suppression in the power spectrum, 1-to-1, I might be able, if I could do this spectroscopy, but I don't think we're going to be able to do that with the current data for neutrino masses for sure. So are there any other ways to expand the parameter space enough to capture the main degeneracies?
One good reason to do these high redshift surveys, either in optical or radio, is that you do it deep in matter domination era. And so now, even if you allow W to be a free parameter, which you would take a big hit from CMB or low redshift on neutrino masses, now you get back this information because you're doing this deep in the matter era. So I see this as a motivation to do very high redshift surveys. Once you free W, then if you have high redshift leverage, your constraints are actually quite good again. I guess, Julien, you also had something along those lines in one of your paper, right?
Yeah, redshift 20. Yep.
No,
So Cora was saying, if we measure a neutrino mass in the future from these experiments, will we really believe it? But now we are a bit in the opposite situation. The error bar is going down, and the preferred value of the neutrino mass when you feed the data is still 0. And 0.06 is around almost the 1 sigma range and is not preferred. So do you think, is any of you getting worried by this? Do you think it's time to get worried, or it's just because there are too many uncertainties? No reactions?
it's tough.
Yeah. Personally, I'm a bit surprised that none of the current experiments return a posterior which is non-zero, because the error bar is so small that it should be the case, unless there is an overall systematics that we don't understand and that systematically pushes the posterior lower than it is. Or, of course, unless there are no massive neutrinos around, which would be a big revolution.
I think we might have to worry soon. I agree. When we start ruling out, if we start ruling out inverted ordering, we might have to worry, because then it has implications.
Sorry, just to understand one thing that I think I didn't get. So when you're saying that you can rule out invert ordering, is like you are assuming lambda CDM, or like you?
Yeah.
Usually, the forecasts are done assuming lambda CDM or some very minimal extension, like adding a W to lambda CDM.
I see.
The errors tend to get worse the more ingredients you add, of course. And
Okay.
that is an important question, is how many ingredients should I theoretically add to get robust constraints? But in principle, I don't have to add all of them if they are not, like the data may not want a W. Why do I have to marginalize over W?
Well, I mean, I guess before saying that you exclude inverted hierarchy, in principle, you should marginalize over all the degenerate parameters, no?
Yes, but there's an infinite amount of things that are degenerate, right?
Yeah, sure.
So
Actually,
W is one that we know is degenerate, but they could also be, you could marginalize over every single piece of BSM physics that you can think, including the running of the tilt, including, whatever.
Yeah, the
Which
running
ones would
of
you
the
actually?
tilt is important. Yeah.
oh, actually, a related question. So if you have two neutrinos that are a little bit heavier, so you have two free streaming scales, then do you get two bumps inside the spectrum? And do you guys currently look for such a feature as well?
Yeah, so we actually, this is a paper, Julien wrote a paper about this, and we did as well, and how you actually distinguish the hierarchy from cosmology alone. And it's very, 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 very hard. That's three varies, one for each neutrino. Because turns out that we're most sensitive to the sum of the masses. And if there's, the masses are similar enough that they just add up to each other. Like essentially, if you had, say that you have the inverted, you have like 2.05 EV neutrinos and 1 0, that just looks like two massive neutrinos. And if you have the normal, it looks like one massive neutrino and like light one. So the amount of precision you will need to tell the hierarchy just from cosmology at fixed mass, you will need very large precision.
And this is true for the entire range that you show in your plots. Is that right?
What do you mean the entire range?
So there's those plots that have that elbow that show some neutrino masses versus the lightest neutrino, I believe. So for any of those set of parameters, you have this issue that you would kind of always be able to really, there's a huge degeneracy there. There's no notion of trying to see two kind of free streaming lengths, so to speak, inside the data.
Yeah, that's right. So the issue is at very high masses, which is where you would actually get a high significance detection, they're the same. And then once you go to lower masses and the signal is weaker, when they actually deviate, it's very hard to distinguish them.
I see, thanks.
So if these two curves were different up here, we would be great. But by construction, they're not.
Yeah, I completely agree with Julien. In principle, you would have a superposition of two steps, but they are so smooth that you cannot see it unless you can resolve the matter power spectrum with a precision of 1 per mil, which is totally futuristic. So it sounds impossible to do in practice.
Can I just add that what Julien just said, the question that he raised applies exactly in the same way to an effective. If you start marginalizing over YP, over W, over all sorts of things, the ineffective bound just goes away. It won't stay. So also there, we have to ask ourselves, if we have a detection of an effective, what do we make about it? So this is something important to keep in mind.
Mm-hmm.
But an effective has some very peculiar signatures, like on the scale of the CMB peaks. So I don't think if you include the CMB data, in particular very good polarization CMB data, I don't think it would remain degenerate with lots of parameters.
You're talking
It's
about
not only
the
a
free streaming,
suppression,
right?
but it's a phase shift, yeah.
Yeah, but
Phase
I thought
shift,
the significance of the phase shift detection of an effective is much, much, much weaker.
Yeah, super small.
It is much weaker, yes, but it should be there. So
Yeah.
Right, but I guess it's a question of whether the delta and effective bound is 0.2 or a 1, right? I think that's what Emanuele was saying. If all this background and effective effects, I can say they're degenerate with things, I can marginalize over them. The significance that I get from the phase shift is very weak. So you get a very, very weak constraint.
Mm-hmm.
I guess one question for the particle physicists in the audience is, why should I care about having different effective between BBN and CMB recombination? I see that some models exist. I don't know what the feelings are about these models from the people there.
perhaps we could change gears a little bit now and talk about I was going to say the big elephant in the room, but it's not the big elephant in the room since it has been mentioned before, which is foregrounds. Emanuele gave a very nice talk about beautiful things that we can do with 21 centimeters and exposed optimistic and pessimistic scenarios. But I would like to talk a little bit more about, our assumptions of the foregrounds being smooth, what we would need to do to, at what level do we need to understand the foregrounds and what do we know now and how can we get more information about them?
I don't know, Julien, do you have more first-hand information from the head analysis?
Not a lot. I mean, so far, the way the HERA has been approaching foregrounds is to throw out anything that is remotely touching foregrounds. And that means that you have to throw away 99-something% of the data. When you do the forecast for Puma, I imagine you do something like that as well, right? Like you throw everything in the wedge.
Yeah, I think we throw away like 50%, yes. Because at low redshift, this wedge is less of a problem.
Right, but we haven't measured at low redshifts, right?
Right. No, of course.
Because at redshift 6, we do have measurements of the wedge. We can characterize it and measure it because it's been, they've been trying this for decades. So I guess the question is, is there any foregrounds above the wedge? Could you have to worry about things leaking into the main data?
Exactly, that was my question. Yes.
And for EOR and Cosmic Dawn, there's been a lot of theoretical and analytical work and also data analysis trying to extract this, trying to see if there's been any foreground leakage and how you prevent it. And one of the issues seems to be that you need to do calibration much better than you think you do. If your antennas are slightly miscalibrated, you end up with foregrounds spilling out. So there is a large cost to things with many antennas. So for HERA is 350, they seem to have it under control. But if you have an experiment with thousands of antennas, calibration seemed like it might be a big nightmare to get to the precision levels that you need.
And indeed, in our proposal of Puma or in general, this next generation of 21 centimeter, there is always some sort of 5 to 10 years of R&D that needs to be done before we sort of start to build it, because all these questions need to be answered before we build it, because it has to be done in real time, for instance, right? You cannot just save, hundreds of petabytes of data per day and then calibrate in post-processing. You have to do it on the fly. So
in the case of HERA, there's been a lot of benefit from having predecessors, like smaller experiments that were built before, like paper, that actually measure these foregrounds, so then you can measure cosmology with HERA. Like, you guys have Chime, I imagine,
there is Chime, there is Hyrax. So we would like to learn from them if and when they make a detection.
Right. So what's the status? Do you know what the status of those are?
Well, Chime is fully built and they've taken data. They have a cross-correlation measurement as well coming up within the next few months. This is what I'm told, again, with DBOS data. And Hyrax is still being prototyped, so I don't think there is much there to be said. Hopefully, Chime will also attempt their own autocorrelation measurement. You will see.
Yeah, I'd be curious to see what their foreground wedge looks like, to see which of your scenarios Puma would be in, because I think that's something you can figure out well before you build it. Right.
No, that's interesting because Chime is this very completely different configurations with cylinders, right? So I guess the community has a bit moved on from cylinders because they are more complicated for these reasons that we just talked about. But it would be nice to see how things will look like for cylinders as opposed to dishes.
I also wanted to ask you, rather than just looking at foregrounds which catch the low K-wave numbers, you had this nice plot when you cut the high K-wave numbers from perturbation theory. Does this include just regular perturbation theory, like EFT, FLSS, or you also have to worry about biases? Like, do we understand galaxy bias at redshift 5? say?
No, yeah, so those cuts are extremely pessimistic, and those come from, as Julien already said, myself being very pessimistic, and also Martin can be very pessimistic about things. So there is a cut which is coming from the nonlinear scale and sort of how well you can do one loop perturbation theory ab initio. And then there is a cut which is actually stronger, which is due to nonlinearities in Rashi space distortions, which is taking a big hit. So the red one was coming from nonlinearities in RSD. And this is super conservative as well, that we're doing from Fingers of God. So the red one will very likely stay. Hopefully, if we can do two loop perturbation theory and things like that, maybe we can sort of do better away from Fingers of God.
And so do you have to worry about galaxy bias being different and being more complicated at high redshifts?
Well, the bias expansion is basically given by symmetries, right? So you just have to write at the given order and perturbation theory all the operators which are compatible with the equivalence principle and rotational invariance. So as long as you have all of them, then we already have all of them, so we keep them, all of them. So the only one which could be a problem are these ones which are coming from radiative transfer. And those ones, we do not include them yet. And we could, and they will spoil us constraints on FNL local, because those are extremely low K.
Those come out during reionization, I guess, redshift 5 and 6.
Yeah.
I'm sorry, I will have to disconnect soon. Maybe I can ask a last very general question from my side to the speakers, but also to experts on the audience, on the theory of large-scale structure. It seems we have seen with many papers, recent papers, that the theory of large-scale structure is mature enough to fit galaxy redshift surveys of the generation of BOSS. Do you think that it's also already mature enough for modeling nonlinear effect first in the next generation, like DAISY, Euclid, Rubin, and then for PUMA and SKA and radio astronomy survey? And if not, where do you think the most of the progress should be done? Maybe Emanuele wants to say something, maybe Julien, maybe Paolo in the room, I don't know.
I guess for current generation, we're fine. I think maybe even the next one. For this decade, I think we're good. For next decade, I'm not so sure. For next decade, it might be worth thinking about. Of course, I guess implicit in this discussion that we're having is that we're only looking at power spectrum. Because for bispectrum, even data that we already have is too good for the perturbation theory model that we have. So we can only do two-point functions very well. Beyond that, we can't really do that. Mm-hmm. Which means we cannot do PNGs, which is something important to many of us.
Another reaction?
So I had a comment on this delta and effective question that you made, Emanuele. Sorry, I mean, it's just, I mean, you should not think of the bound from BBN and CMB as degenerate at all from the particle physics perspective. One example is just light dark matter freeze out, no? So you could inject some relativistic species just
after BBN.
Yeah, I mean, yeah.
No, I guess you can model building of that you can do, but why would you do it?
I mean, this is a question that people stepped into independently on this result that you guys showed today, just because they were interested in making dark matter freeze out at light masses. So it appears somehow,
Because I would think that, I don't know, if you want to have some non-standard BBN where there are new interactions, regardless of new light degrees of freedom, that is also one scenario in which you want to separate delta and effective at BBN and recombination.
Yeah, I mean, in this case, you just have a late time injection. That's what I'm. David, you wanted to?
I'm going to ask a related delta and effective question. Is it okay? This is David. Thanks for the nice talks and discussion. I wanted to ask a delta effective related question again, just while the experts are here. It's kind of open-ended. Do you have an opinion on what, I don't know, on multi-decade timescales even, what the best delta effective constraint is that we might possibly get given the available data? So CMB, the cosmic variance limit seems to be like 1 or 2%-ish. And then, Emanuela explained, explained to me that the, 21 centimeters is not the magic that I thought it was. Are we stuck with sort of percent? Is there any way to get to 0.5% or less? Any chance at all in any way, in any principle?
So if you look at our optimistic scenarios, where you make a bagel of all possible large-scale structure surveys, you can do 0.5%. But this is, I personally think this is realistic, because it means that you can combine all sorts of data from all surveys from today within the next 20 years and just combine them and get a number out of it.
I see. So that's like reducing the number of parameters you have to marginalize over and blah, 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 and then you can get down to half, maybe.
Yeah, but I guess below percent, I find it very hard to believe, yes. I think Cora is saying no with the.
So Cora's saying no to better than 1% ever?
It sounds pretty impossible, yeah.
Sorry, possible as in, wait.
No, I mean, it sounds, it doesn't sound realistic. No,
Right.
Hi, David, by the way.
Oh, hi, good to see you, Cora. Yeah. Yeah, no, that's fair. That's kind of what I feared, but I just wanted to see if there was some sci-fi scenario in the technological imaginable future, but maybe not.
I mean, if you go to the far future of humanity and you go dark side of the moon, that sort of stuff, perhaps.
Wait,
we're not talking about lifetime, like lifetime scales.
Yeah, like within my lifetime, are we going to get delta effective less than 1%? Yeah.
I agree. I also don't think so.
Thank you.
Okay, if there are no.
Yes, I was going to say we lost Julien and we are about to lose myself too.
No, I think we can close this discussion. Yes, I think it's if there are no other pressing questions.
Well, let me thank also the speakers for very nice talks.
Yeah, let's thank all of us. Thank the speaker. And thank you very much, Cora, for helping with the discussion. We didn't have the chance of thanking Julien, so.
Thanks, Julien.
We are gonna send him an email.
This recording.
Bye-bye.
Bye-bye,
Enjoy
thanks.
Florence.
Ciao.
Bye, everyone. Take care.
Ciao.